Welcome to Spring LIB.
Let us look at a problem of a ball bearing. So in a ball bearing, you have an inner circle, which is sometimes also called race. So this is the inner race, let's call it A. And then there is an outer race called B. Let's call it B. And then in between these two races, we have solid balls on which A can slide with respect to B. So this is basically the structure of a ball bearing. So the diameter of A is given to be 60 millimeters, and diameter of each ball is given to be 12 millimeters. So, half of radius of A will be 30 millimeters, and then radius of B will be radius of A plus diameter of ball, which will be 30 plus 12 equals 42 millimeters, since everything is in millimeters. Okay, so now it is given that A has an angular velocity 3600 rpm, rotations per minute. So omega A is 3600 rpm, and we are also given that B is stationary, which means it's not moving. Okay, so then we are asked what is the velocity, what is the velocity of center of each ball, so or speed of center of each ball, because direction will be different based on where the ball is. So speed of ball is unknown, and we also need to determine omega of balls. Okay, so again, as I repeat in every problem, there are two principles. You break the motion in translation and rotation, and points of contact have same velocity. Okay, so let us analyze one of these small balls. So let's say here is a small ball, and since all these balls are symmetrically placed, if you solve for one ball, basically you have solved for all the balls. So the velocity of this point, since this is in contact with A, so let's call this point ball at contact A. Now, since the velocities at the point of contact have to be equal, the velocity, the rotational velocity, let's write down here, is going to be, so since A is moving like this, so it doesn't matter what direction you choose. Basically, if your maths is correct, the final answer you get will be correct, but we'll just try to include the correct answer. So since the A is moving like this, the balls, I think, will move like this. So in that case, omega will not point along this direction. So omega will point along this direction, omega r. So this is the radial velocity. So radial velocity is always omega cross r, which in this case, since it's perpendicular to our radius vector here, so this velocity is coming from the disk A. It's in contact with disk A, which I'm not drawing here, but just showing you. So this is going to be the r. So omega cross r is perpendicular here, and the value is going to be 3600 rotations per minute. So basically this is 3600 times 2 pi radians divided by 60 seconds. So these many radians per second times radius, and the radius is 30. So 30 cancels this, you get 2, then this cancels this. So it's 3600 sorry, there wouldn't be any 3600. Yeah, 3600 rotations per minute. So 3600 times pi radians per second. This is the velocity at point BA, let's call this. Now, the point of ball bearing which is touching point B, let's call this point BB, this we know that it has a velocity 0. Now, if the velocity at point BA is 3600 pi radians per second, what is the velocity of the ball bearing? So this tells us, since VBA equals 3600 pi radians per second and it's pointing up, the same velocity of radial velocity is going to point down here as well, because since it's a circle, the omega r is going to be same if it has a different omega than omega a. So let's just call this omega a. This will be a different omega, but the omega of ball times radius of ball will be equal to this value. Only the direction of omega will change at each point. So since it was pointing up here, it will point down here, and then it needs to have some translational velocity to cancel this, because we know that points in contacts have same velocity. So since B is stationary, 3600 pi times radians per second has to equal Vt. So this is the speed of the ball by which it's moving up or down. So this is speed of the ball. There should be a length unit somewhere here. Yes, here. So it was millimeters here. So millimeters, and this will be millimeters. So if you want to convert this into meters per second, then you can divide it by 1000. So this will be 3.6 pi meters per second. That will be your Vt. So it's always good practice to check your units so that you make sure you don't make a mistake. So here millimeters, I didn't write it down explicitly, so I put it back down. So velocities have to be in the units, distance over time, and angular velocities have to be in units 1 over time, because radians are dimensionless. Okay, so we have figured out speed of the ball. Now, how many rotations are these balls making per minute, or what is the omega of the ball? So for omega of the ball, now, as I said, this was omega A R A. So omega A R A actually is equal to omega B R B. This has to be because the velocity at the point of contact BA has to be same. So VBA is point of contact. We have already used this to solve for VT. So basically what this gives us is omega A was 3600 rotations per minute times RA. RA was 50 millimeters, sorry, 30 millimeters, and then omega B, which we don't know, and then RB, we know it's going to be, the diameter was 12, so radius of ball will be 12 by 2, 6 millimeters. So we can use that here. So this will be omega B times 12 millimeters. Let me write this slightly more nicely. 12 millimeters, millimeters cancel. Then omega B is simply 12 can cancel 3600 because 12 threes are 36. So omega B is going to be 9000 rotations per minute. But you can also write this down in terms of radians per second by just converting it as 9000 times 2 pi, these many radians in one rotation, then divided by 60 seconds. So 0 is cancelled and 6 can cancel this by 150. So you have 300 pi radians per second. So this is omega p. So we have figured out omega b and speed of the ball by using the principle of breaking all the motions into translation plus rotation. This was the rotational motion, and this was the translational motion, which is required to cancel the speed because we knew that v is stationary. So vt had to be equal to this 3600 pi radians per second. So we got speed of the ball using this, and then since we know at the point of contact of A the velocities are equal, so we calculate it from the circle of A, and then circular motion of A and circular motion of B have to give the same value. We equate that, use the correct radii, and we finally get the value of omega p.